In January of 2026, a team of astronomers published the sharpest image ever produced of something that nobody has ever seen. Not a distant galaxy, not a black hole shadow, not a nebula lit up by dying stars. They mapped the invisible scaffolding that holds the entire universe together. The image came from the James Webb Space Telescope, and it showed dark matter, the substance that makes up roughly 85% of all matter in existence, stretched across billions of light years in a web of filaments and nodes and vast empty voids, all rendered at twice the resolution of anything that came before it. The team measured the shapes of 129 galaxies in every square arc minute of sky they observed. That is nearly double what the Hubble Space Telescope could manage, and more than 6 times what any ground-based telescope has ever achieved. By tracking the tiny distortions in those galaxy shapes, distortions caused by the gravitational pull of matter we cannot see, they reconstructed what amounts to an X-ray of the cosmos, the bones of the universe laid bare, and the picture is exactly what our best model of the universe predicted it would be. Galaxies cluster at the dense intersections of dark matter filaments, like water pooling at the joints of a spider's web. The filaments stretch between those clusters across hundreds of millions of light years. In between, there are voids, regions where almost nothing exists. The structure is beautiful, it is intricate, and it matches our theoretical predictions with stunning fidelity. So here is the question that makes this moment so extraordinary. If the map confirms what we expected, why are so many physicists more nervous now than they have been in decades? Because confirmation at this level of precision is a double-edged sword. The same instruments that validated the scaffolding have also revealed cracks, not in the scaffolding itself, but in the model that predicted it. Other measurements, taken by other telescopes using other methods, are returning numbers that disagree with each other. The universe appears to be expanding at 2 different speeds, depending on how you measure it, and the discrepancy is now so large that the odds of it being a statistical fluke are less than 1 in 3.5 million. Some observations suggest the universe is less clumpy than our model says it should be, though the latest analyses have walked that particular tension back. And brand new data from a survey of 11 million galaxies hints that dark energy, the force accelerating the expansion of space, might not be constant at all, but changing over time. 93 years ago, a physicist who was widely considered to be one of the most difficult human beings in the history of science looked at a cluster of galaxies and realized that the math did not work. The galaxies were moving too fast. There was not enough visible matter to hold them together. Something massive and invisible had to be there, or the entire cluster should have flown apart billions of years ago. He called it dunkle materie, dark matter, and almost nobody believed him. What followed is one of the strangest detective stories in the history of physics. It involves a Swiss-Bulgarian immigrant who called his colleagues spherical bastards, a woman who was denied access to telescopes because there was no ladies' bathroom, a priest who derived the expanding universe before anyone else and was told by Einstein that his physics was abominable. And it all converges on this moment right now, when the sharpest map of the invisible universe ever created arrives at the precise instant that our best model of reality is under more pressure than it has faced in its 40-year reign. The question is not whether dark matter exists. That debate ended years ago. The question, the one that every section of this story will try and fail to fully answer, is whether we actually understand what it is doing. Whether the model we built to describe it, a model so successful that it predicted the temperature of the cosmic microwave background to 5 decimal places, is the final word, or whether 93 years of searching have brought us to the edge of something we do not yet have the physics to explain. This is a story about the invisible architecture of reality, and every answer we have found so far has only made the question bigger. The man who started all of this was Fritz Zwicky, and to understand why it took 4 decades for anyone to take his discovery seriously, you need to understand what Fritz Zwicky was like as a person. He was born on Valentine's Day, 1898, in the city of Varna, Bulgaria, to a Swiss father and a Czech mother. When he was 6, his parents sent him to Switzerland to be raised by his grandparents, and he stayed there through his entire education, earning a doctorate from ETH Zurich in 1922 under the supervision of Peter Debye and Paul Scherrer. 3 years later, he emigrated to the United States on a Rockefeller Foundation fellowship to work with the Nobel laureate Robert Millikan at Caltech. He never left. From 1925 until his death in 1974, Caltech was his home. And by nearly every account from the people who worked with him, those 5 decades were marked by a level of interpersonal hostility that is genuinely difficult to exaggerate. His most famous phrase survives in multiple versions, but the core of it is consistent. He called his colleagues spherical bastards. Richard Preston, in his book First Light, recorded Zwicky's explanation. "They are spherical," he said, "because they are bastards every way I look at them." Robert Kirshner, the Harvard astrophysicist, recalled a separate incident. In 1933, "I told those no-good spherical bastards that supernovas make neutron stars," Zwicky told him. "Now they find these damn pulsars, and nobody gives me the credit." His daughter Barbarina later disputed this, claiming he used the phrase only twice and only about Swiss politicians. But the independent recollections from Preston, Kirshner, and Jesse Greenstein, who was chairman of Caltech's astronomy department, all tell the same story. Zwicky had a talent for alienating everyone around him. His feud with Walter Baade, a German astronomer who was genuinely one of his most important collaborators, was legendary. During the Second World War, Zwicky called Baade the Nazi. Baade, who had in fact stayed out of politics and was classified as an enemy alien by the United States government, reportedly told colleagues that he was genuinely afraid Zwicky would kill him. When a rattlesnake appeared in Zwicky's telescope dome at Palomar, Zwicky accused Baade of planting it. Jesse Greenstein, who observed all of this firsthand, said simply, "I disliked him as a human being. He was vain and very self-centered." Kip Thorne, one of the most respected physicists alive, described Zwicky as someone whom many of his colleagues regarded as an irritating buffoon. By the end of his career, Zwicky was banned from using the 200-inch Palomar telescope and was working from a basement office. His daughter remembered that everyone at Caltech would scatter when Daddy and I would walk down the hallway. This matters because it is inseparable from the science. Zwicky did not simply discover dark matter and receive polite skepticism. He discovered dark matter and was so personally toxic that the entire astronomical establishment had extra motivation to ignore him. The tragedy of Fritz Zwicky is that he was right about almost everything and wrong about almost everyone. And because he was wrong about the people, the things he was right about took decades longer to be accepted than they should have. In 1933, Zwicky published a paper in Helvetica Physica Acta with the title Die Rotverschiebung von extragalaktischen Nebeln, which translates to the redshift of extragalactic nebulae. He was working with redshift data that had been published by Edwin Hubble and Milton Humason, studying a collection of galaxies called the Coma Cluster, a massive structure of over 1,000 galaxies sitting roughly 321 million light-years from Earth. The data he had was sparse, just 7 galaxies with measured velocities. But Zwicky did something clever with them. He applied the virial theorem, a mathematical relationship from statistical mechanics that connects the average kinetic energy of a gravitationally bound system to its gravitational potential energy. In plain terms, if you know how fast the objects in a system are moving, you can calculate how much total mass must be present to keep them gravitationally bound. If there is not enough mass, the system should fly apart. Zwicky measured the velocities of those 7 galaxies and compared the mass implied by their motions to the mass he could estimate from visible light. The discrepancy was enormous. The cluster needed at least 400 times more mass than the luminous matter could account for. His conclusion, written in that 1933 paper, was direct. If this were to be confirmed, the surprising result would then follow: that dark matter is present in very much greater density than luminous matter. Now, there is an important caveat here that Zwicky himself could not have known about. His factor of 400 was an overestimate, and significantly so. The reason was that he used a value for the Hubble constant that was far too high, which threw off his distance and mass calculations. Modern data, using over 1,000 radial velocities rather than 7, puts the actual ratio at about 5 to 1. Dark matter outweighs visible matter in galaxy clusters by roughly 5 times, not 400. But the fundamental insight was correct. There is far more matter in these systems than anything we can see. The specific number was wrong. The physics was right. And essentially, nobody cared. Zwicky published a follow-up paper in 1937 in the Astrophysical Journal titled On the Masses of Nebulae and of Clusters of Nebulae, refining his analysis and, almost as an afterthought, predicting that galaxies would act as gravitational lenses, bending the light of more distant objects. He estimated about a 1% probability of observing such lensing. That prediction was confirmed in 1979 with the discovery of the twin quasar, 5 years after Zwicky died. But the dark matter result sat there for decades. It was not that the physics community actively rejected it, so much as they simply did not engage with it. Zwicky was difficult. His colleagues avoided him, and the idea that most of the matter in the universe was invisible seemed, at the time, like exactly the kind of wild claim you would expect from a man who called everyone spherical bastards and accused people of planting snakes in his telescope dome. The frustrating thing is that Zwicky's scientific range was extraordinary. In 1934, Working with Bardet despite their mutual animosity, he presented 2 papers at the Stanford meeting of the American Physical Society that Kip Thorne later called one of the most prescient documents in the history of physics and astronomy, published in the Proceedings of the National Academy of Sciences. These papers coined the term supernova, predicted the existence of neutron stars just 2 years after the neutron itself had been discovered, and proposed that cosmic rays originate from supernovae. He personally discovered 120 supernovae over the course of his career, a record that stood for 35 years. He held more than 50 patents in jet propulsion, and he died on February 8, 1974, 6 days before his 76th birthday, in Pasadena, California, without seeing any of his most important predictions confirmed. Neutron stars were found in 1967 with the discovery of pulsars. Gravitational lensing was observed in 1979, and dark matter did not become a pillar of cosmology until the early 1980s, largely through the work of a woman who faced obstacles that were different from Zwicky's, but in some ways just as absurd. Vera Florence Cooper Rubin was born on July 23, 1928, in Philadelphia, to parents who had emigrated from Lithuania. She became fascinated with the stars when she was 10 years old, watching them from her bedroom window. By the time she was 14, she had built her own telescope from a cardboard tube and was tracking meteor paths on the hand-drawn star charts. She graduated from Vassar College in 1948 as the sole astronomy major in her class. She applied to Princeton's graduate program in astrophysics. Princeton rejected her, not because of her qualifications, because the program did not admit women. That policy remained in place until 1975, almost 3 decades later. So she went to Cornell instead, where her master's thesis advisor was Philip Morrison, and she attended lectures by Richard Feynman and Hans Bethe. Her thesis was ambitious. She was investigating whether the distribution of galaxies showed signs of large-scale rotation beyond what was expected from Hubble flow, the general expansion of the universe. It was a good question. It was also, as far as the astronomical establishment was concerned, an unwelcome one. When she presented her results at the 1950 American Astronomical Society meeting, she was ridiculed by prominent male astronomers. Her thesis advisor, William Shaw, offered to present the findings under his own name, since Rubin was pregnant and not an AAS member at the time. She refused. "That's okay," she said. "I'll do it." Both the Astrophysical Journal and the Astronomical Journal rejected her thesis for publication. She moved on to Georgetown University, where she earned her doctorate under George Gamow, one of the founders of Big Bang cosmology. Her doctoral dissertation concluded that galaxies tend to clump together rather than distributing randomly through space. This result was largely ignored by the field and would not be confirmed until the 1970s. Gamow himself, for all his brilliance, told Rubin that they would have to discuss her work in the lobby of the building because women were not allowed in the office area. This is the environment in which Vera Rubin operated for the first 15 years of her career. Not a hostile environment in the overt sense. Nobody was shouting at her or calling her names, the way Zwicky had done to his colleagues. It was something quieter and in many ways more suffocating. She was simply excluded. The telescopes were off limits. the journals were unreceptive. The professional spaces where science happened were spaces where women were not supposed to be. In January of 1965, Rubin joined the Carnegie Institution of Washington's Department of Terrestrial Magnetism as its first woman staff scientist. And there, she met the person who would make everything possible. Not a mentor in the traditional sense, an instrument builder named W. Kent Ford Jr. Ford had constructed something called the DTM image tube spectrograph, a device that increased the sensitivity of telescopes by a factor of 10 or more, where previous instruments needed long, fragile photographic exposures to capture the faint light of distant stars. Ford's spectrograph converted photons to electrons and amplified the signal electronically. It was, for its time, like upgrading from a candle to a spotlight. That instrument now sits in the Smithsonian's National Air and Space Museum. What Rubin wanted to do with Ford's spectrograph was simple in concept and extraordinary in execution. She wanted to measure how fast stars and gas clouds at different distances from the center of a galaxy were orbiting. This is called a rotation curve, and in 1965, nobody had measured a really detailed one for any galaxy beyond our own. The expectation, based on Newtonian gravity and the distribution of visible light in galaxies, was straightforward. Stars near the center of a galaxy should orbit quickly because they feel the gravitational pull of the dense core. Stars farther out, where the visible matter thins out, should orbit more slowly, just as the outer planets in our solar system orbit the Sun more slowly than the inner ones. Mercury travels at about 47 kilometers per second. Neptune crawls along at about 5.4. The relationship between distance and speed is called Keplerian decline, and it is one of the most basic predictions of gravity in any system where mass is concentrated at the center. Rubin and Ford started with the Andromeda Galaxy, our nearest large galactic neighbor. They published their results in 1970 in the Astrophysical Journal. Using Ford's spectrograph, they had measured the velocities of 67 hydrogen emission regions across Andromeda, from the inner core all the way out to 24 kiloparsecs from the nucleus. The inner galaxy behaved as expected. They found a maximum circular velocity of about 225 kilometers per second near the center, then a deep minimum around 2 kiloparsecs out. So far, so normal. But then something strange happened. As they moved farther from the center into the dim outskirts, where the visible stars thin out to almost nothing, the velocities did not decline. They stayed flat, 226 kilometers per second, out and out and out, as far as they could measure. Radio observations later extended these measurements to 35 kiloparsecs, roughly 114,000 light-years from the center. The velocities stayed flat the entire way. Think about what that means for a moment. If you could somehow stand at the visible edge of the Andromeda Galaxy and measure the speed of the last stars you can see, they would be orbiting at roughly the same speed as stars deep in the galactic core. That is not possible if the galaxy's mass is concentrated where the light is. The only explanation is that there is an enormous amount of mass extending far beyond the visible galaxy, mass that you cannot see, pulling on those outer stars and keeping their velocities high. But one galaxy could be an anomaly. Maybe Andromeda was special. Maybe something about its particular history or environment produced unusual rotation. The real test was whether this pattern repeated. So Rubin and Ford did what any good experimentalist would do. They went looking for more galaxies. The definitive paper came in 1980. Rubin, Ford, and their colleague Norbert Thonard published a study of 21 spiral galaxies spanning radii from 4 to 122 kiloparsecs. The result was devastating in its simplicity. Every single galaxy showed flat rotation curves, not a few of them, not a statistical tendency, all 21. Rubin's conclusion was characteristically direct. The conclusion is inescapable that non-luminous matter exists beyond the optical galaxy. The mass required to explain the flat curves was roughly 10 times the visible mass. Every galaxy they examined was sitting inside an enormous halo of invisible matter, a halo that extended far beyond the stars and gas that telescopes could see. By the early 1980s, Rubin had studied over 200 galaxies and published over 200 papers. The dark matter that Zwicky had glimpsed in the Coma cluster 47 years earlier was not an anomaly confined to galaxy clusters. It was everywhere, every galaxy, every system. The universe was drowning in invisible mass. But here is the problem that Rubin's data created, a problem that is still with us today. Her rotation curves prove that dark matter exists. They proved it overwhelmingly, in galaxy after galaxy, with impeccable data. What they could not tell us, and what nothing has yet been able to tell us, is what dark matter actually is. Rubin could see its gravitational fingerprint in every galaxy she observed. She could calculate its mass. She could map its distribution. But the substance itself remained completely invisible, completely undetectable by any instrument other than gravity. She had proven beyond any reasonable doubt that 85% of the matter in the universe is something we have never touched, never captured in a detector, never produced in an accelerator, and do not understand at the level of particle physics. That is not a comfortable position for a science that prides itself on building things from first principles. And the way the world treated Vera Rubin while she was alive makes that discomfort feel personal. When she first applied to observe at the Palomar Observatory in 1965, home to the 200-inch Hale telescope, the most powerful telescope in the world at the time, she was told that her time on the observatory would be limited because there was no women's bathroom. Rubin's response was characteristically practical. She cut out a paper figure of a woman in a skirt, taped it over the stick figure on the men's room door, and said, "There you go. Now you have a ladies' room." She became the first woman officially permitted to observe at Palomar. The honors came eventually. She was elected to the National Academy of Sciences in 1981, only the second woman astronomer to receive that distinction after Margaret Burbidge. She received the National Medal of Science in 1993. In 1996, she won the Gold Medal of the Royal Astronomical Society, the first woman to receive it since Caroline Herschel in 1828. That is a gap of 168 years. But the Nobel Prize, the one that would have validated not just her work, but the fundamental shift she imposed on our understanding of the cosmos, never came. The 2011 Nobel went to the discoverers of dark energy, a phenomenon that, like dark matter, has never been directly detected as a particle. The 2019 Nobel went to James Peebles, for theoretical cosmology work that directly complemented what Rubin had observed. Emily Levesque of the University of Washington called the omission glaring. It was. Vera Rubin died on December 25, 2016, at the age of 88. The Nobel Prize is not awarded posthumously, so the question of whether she deserved it is now permanently academic. Matthew Scott, president of the Carnegie Institution, called her a national treasure. Her own assessment of her legacy was, as always, more measured. "Fame is fleeting," she said. "My numbers mean more to me than my name. If astronomers are still using my data years from now, that is my greatest compliment." They are. In December of 2019, Congress formally renamed the Large Synoptic Survey Telescope, a massive new observatory under construction in Chile, as the Vera Rubin Observatory. It is the first national observatory in the United States, named after a woman. When it begins its full survey operations, it will map dark matter across the sky with a 3,200 megapixel camera, the largest digital camera ever built, mounted on an 8.4-meter primary mirror. The observatory that bears her name will spend a decade doing exactly what she spent her career doing, only across the entire visible sky. But the problem her data created has not gone away. We know dark matter is there. We know how much of it there is. Roughly 5 times the mass of all visible matter combined. We know it forms enormous halos around galaxies and stretches in filaments between galaxy clusters. What we do not know, and what Rubin's rotation curves could never tell us, is what it is made of, how it interacts with itself, and whether the model we have built to describe its behavior is the right one. Zwicky saw the shadow in 1933. Rubin proved it was everywhere in 1980. But proving that something invisible exists is very different from understanding it. And to have any hope of understanding it, physicists needed a way to see dark matter directly, not through the stars it influences or the galaxies it holds together, but through its own gravitational signature written on the fabric of space itself. That tool already existed. It had been predicted by the same man who told a Belgian priest that his physics was abominable. In 1915, Albert Einstein completed the general theory of relativity, which replaced Newton's idea of gravity as a force with a radical new picture. Mass and energy do not pull on objects. They curve the geometry of space-time, and objects follow the straightest possible paths through that curved geometry. One of the theory's many predictions was that a sufficiently massive object would bend the path of light passing near it, acting like a lens. Einstein calculated that light just grazing the edge of the sun would be deflected by 1.75 arcseconds. That is a tiny angle, roughly the apparent size of a tennis ball viewed from 10 kilometers away. But it was twice the value that Newtonian gravity predicted, and the difference was enough to test. The test came during the total solar eclipse of May 29th, 1919. 2 British expeditions set out to photograph stars near the eclipsed sun. Arthur Eddington led one team to the island of Principe, off the west coast of Africa. Andrew Crommelin led the other to Sobral, Brazil. The eclipse blocked the sun's glare, making it possible to see and photograph background stars whose light passed close to the sun on its way to Earth. On November 6, 1919, The results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The Sobral team measured a deflection of 1.98 arcseconds, plus or minus 0.12. The Principe team measured 1.61 arcseconds, plus or minus 0.30. Both results were consistent with Einstein's prediction. Both ruled out the Newtonian value of 0.87 arcseconds. Einstein was right. Mass bends light. He became the most famous scientist in the world overnight. But the real significance for our story is not the confirmation of general relativity. It is the tool that confirmation handed to future generations of astronomers. If mass bends light, then by carefully measuring how the light from distant objects is bent, you can map the mass that is doing the bending, even if that mass is invisible. Gravitational lensing, as it came to be called, operates at 3 scales, and understanding the differences between them is essential for understanding how the James Webb Space Telescope just produced the sharpest dark matter map in history. Strong lensing is the dramatic version. When a very massive object, like a galaxy cluster, sits between us and a more distant galaxy, the curvature of space-time can produce spectacular effects. The background galaxy might appear as multiple images, or as a ring, or as giant luminous arcs smeared around the foreground cluster. The first gravitational lens was discovered in 1979 by Dennis Walsh, Robert Carswell, and Ray Wayman. They found 2 images of the same quasar, separated by 6 arcseconds on the sky, with a time delay of 417 days between them. The same light, arriving along 2 different paths through curved space-time. Zwicky had predicted exactly this in his 1937 paper. It was confirmed 5 years after his death. Microlensing is the smallest scale. When a relatively low-mass object, something roughly star-sized, passes between us and a background star, the multiple images it produces are too close together to resolve. Instead, the background star simply brightens temporarily. This was used in the 1990s by the Macho and Eros projects to test whether dark matter might consist of dim, compact objects like brown dwarfs or rogue planets lurking in galactic halos. The result was clear. Such objects could account for at most 20% of halo mass. Dark matter is not made of faint stars. But the version of lensing that transformed dark matter research is weak lensing, and it is the subtlest and most statistically demanding technique in modern astronomy. Imagine looking at a distant galaxy through a perfectly transparent universe. That galaxy has some intrinsic shape, probably elliptical to some degree, oriented in some random direction. Now imagine that between you and that galaxy, there is a large concentration of dark matter. The dark matter curves space-time, and the light from that distant galaxy, passing through that curved region, gets ever so slightly distorted. The galaxy appears stretched by about 1%, preferentially in the tangential direction relative to the dark matter concentration. 1%. That is far smaller than the galaxy's own natural shape, which can vary by a factor of 3 to 30. You cannot learn anything from one galaxy. The distortion is too small and the natural shape variation is too large. But if you measure the shapes of thousands of galaxies behind the same foreground region, and you average those shapes, the random natural orientations cancel out. What remains is the systematic tangential alignment imposed by the gravitational field of the foreground mass. through a mathematical technique called the Kaiser-Squires method, developed in 1993. You can convert these shape distortions into a map of the projected mass distribution, including all mass, visible and dark, making no assumptions about what the matter is or how it behaves. You simply measure how the light is bent and work backward to the mass. This is the technique that made the dark matter maps possible, but it is extraordinarily demanding. You need to measure the shapes of galaxies to better than 1% accuracy. You need to subtract the effects of the atmosphere, the telescope optics, and the detector electronics, all of which introduce their own systematic shape distortions that can be as large as the lensing signal itself. You need distances to the background galaxies, estimated from their colors rather than their spectra, because there are far too many to observe individually with a spectrograph, and you need millions of them to beat down the statistical noise. It is, by a comfortable margin, one of the most technically challenging measurements in all of science. And when it works, it reveals the invisible, the most dramatic confirmation of dark matter that weak lensing ever provided came from the Bullet cluster, a pair of galaxy clusters formerly designated 1E0657-558, sitting about 3.7 billion light-years away. What we see there is the aftermath of a collision between two galaxy clusters that occurred roughly 100 million years ago, with the smaller cluster plowing through the larger one at a velocity of approximately 4,500 kilometers per second. This collision created a natural experiment in mass separation. When two galaxy clusters collide, three things happen. The individual galaxies, which are mostly empty space, pass through each other without interacting, like two swarms of bees flying through each other. The hot gas between the galaxies, which makes up the bulk of the ordinary matter in clusters, does interact. The gas particles collide electromagnetically, slow down, pile up, and heat to millions of degrees, glowing brightly in X-rays. And the dark matter, if it exists and interacts only through gravity, should pass straight through without slowing, just like the galaxies. In 2006, Douglas Clow and his collaborators published a paper in the Astrophysical journal Letters with a title that pulled no punches: a direct empirical proof of the existence of dark matter. Using the Chandra X-ray Observatory to map the hot gas and weak gravitational lensing from the Hubble Space Telescope and the Magellan telescopes to map the total mass, they showed that the mass distribution and the gas distribution did not overlap. The gas, the dominant component of ordinary matter, was piled up in the middle where the collision had slowed it down. But the mass peaks, as measured by weak lensing, were offset from the gas by 8 standard deviations, coinciding instead with the galaxies that had passed through unimpeded. This spatial separation cannot be explained by modifying the laws of gravity. If gravity was simply different from what we expect, the mass should trace the matter, all the matter, including the gas. It does not. The mass went where the collisionless component went, not where the gas went. Something massive and invisible and non-interacting sailed through that collision, while the gas was left behind. Dark matter is not a gravitational illusion. It is a substance. And in January of 2026, a new analysis of the Bullet cluster using the James Webb Space Telescope and Chandra together, led by Char and collaborators, used 146 strong lensing constraints and 398 weak lensing sources per square arc minute to produce the highest resolution mass reconstruction of the bullet cluster ever achieved. The separation between mass and gas was independently confirmed yet again at even higher precision. So by the mid-2000s, the evidence for dark matter as a real substance was overwhelming. Zwicky had seen it in galaxy clusters. Rubin had proved it was in every galaxy. The bullet cluster had demonstrated that it was something physical, not a trick of gravity. But what no one had done yet was map its large-scale distribution across the cosmos to see the scaffolding that dark matter supposedly built, the web of filaments and nodes that our best computer simulations predicted should exist. That changed in 2007 through a project called the Cosmic Evolution Survey, or COSMOS. COSMOS was the largest project the Hubble Space Telescope had ever undertaken. Led by Nick Scoville at Caltech, it consumed 590 orbits of Hubble's time, using the advanced camera for surveys to photograph a 2 square degree patch of sky in the constellation Sextans near the celestial equator. 2 square degrees does not sound like much until you realize it is about 16 times the area of the full moon, and that Hubble's field of view is so narrow that covering this area required hundreds of individual pointings stitched together. The survey detected 1.2 million objects, with additional observations from the XMM Newton X-ray telescope, the Chandra X-ray Observatory, and the Very Large Array Radio Telescope, involving over 200 scientists across a dozen countries. The dark matter map from COSMOS was published by Richard Massey and collaborators as the cover article of Nature on January 7th, 2007. The title was simple and direct. Dark matter maps reveal cosmic scaffolding. Using weak lensing distortions of more than 500,000 distant galaxies, the team created the first high-fidelity three-dimensional map of dark matter distribution on large scales, covering 1.6 square degrees of sky and spanning 8 billion light-years of cosmic history. And what the map showed was exactly what the computer simulations had predicted: a loose network of filaments growing over time, intersecting in massive structures at the locations of galaxy clusters. Dark matter formed the skeleton. Ordinary matter collected along that skeleton. Stars and galaxies grew at the densest nodes. Massey summarized the result with the phrase that would define the entire field: dark matter is like the scaffolding of the universe. It was a triumph for the standard model of cosmology. The theoretical framework known as Lambda cold dark matter, or Lambda CDM, predicted that dark matter would form precisely this kind of cosmic web, and the COSMOS map confirmed it in breathtaking detail. The scaffolding was real, the model worked, but the COSMOS map had limitations. Hubble could detect about 71 galaxies per square arc minute, which sounds like a lot until you try to map dark matter at fine resolution. Ground-based surveys were even worse, managing about 20 per square arc minute. At these densities, the dark matter map was blurry. You could see the big filaments and the massive nodes, but the fine structure, the smaller halos, the delicate bridges between clusters, was lost in the noise. To see the scaffolding in real detail, astronomers needed something with far more light-gathering power, far better resolution, and access to the infrared wavelengths where the most distant galaxies radiate their light. They needed an instrument that had not yet been built when the 2007 map was published. They needed the James Webb Space Telescope. JWST launched on Christmas Day of 2021, and by every meaningful metric, it exceeded expectations. Its primary mirror is 6.5 meters across, compared to Hubble's 2.4. Its light-gathering area is 6 times larger. It operates in the infrared from 0.6 to 28.5 microns, which means it can see galaxies whose light has been stretched by the expansion of the universe to wavelengths that Hubble cannot detect. A galaxy at a redshift of 8, meaning we are seeing it as it existed when the universe was about 650 million years old, has had its ultraviolet light stretched to 2 or 3 microns. Hubble is blind at those wavelengths. JWST sees them perfectly. But for dark matter mapping specifically, the advantage is even more fundamental than raw sensitivity. Weak lensing requires measuring the shapes of background galaxies with extreme precision. The more galaxies you can measure behind a given region of sky, the more precisely you can reconstruct the foreground mass distribution. Ground-based telescopes get about 20 galaxies per square arc minute. Hubble manages about 71. JWST, with its mirror and its position in deep space where the atmosphere does not blur images, can see 129, nearly double Hubble, more than 6 times ground-based. That is not an incremental improvement. It is a different regime entirely. The program that exploited this advantage is called Cosmos-Web, and it is the largest general observer survey in the history of JWST. 255 hours of observing time, allocated across 3 epochs in 2023 and early 2024, pointed at the same patch of sky in sextans that the original Cosmos survey had mapped with Hubble. The project is co-led by Caitlin Casey, who holds a faculty position at UC Santa Barbara after beginning the project while at the University of Texas at Austin, and Jehan Kartaltepe at the Rochester Institute of Technology. Casey is a Gates Cambridge scholar who earned her PhD at Cambridge in 2010 and founded the Taurus program for underrepresented undergraduates in astronomy. Kartaltepe specializes in galaxy morphologies and mergers. Their team includes over 100 collaborators, and the data products they have released are shaping practically every subfield of extragalactic astronomy. Cosmos Webb covered 0.54 square degrees with JWST's near-infrared camera, or NIR-CAM, in 4 filters spanning wavelengths from 1 to 4.4 microns, reaching depths of 27.5 to 28.2 magnitudes. It also covered 0.19 square degrees with a mid-infrared instrument, or MIRI, at 7.7 microns. The combined area is approximately 3 times the apparent size of the full moon. That might sound small, but when you consider the depth to which every patch of that area was imaged, the dataset is staggering. The Cosmos 2025 catalog, released in June of that year, provides photometric measurements for over 700,000 galaxies across 37 photometric bands. The dark matter map that emerged from this data was published in Nature Astronomy in January 2026, with Diana Scognamiglio as lead author and Richard Massey, who had led the original 2007 Cosmos map, among the co-authors. The paper is titled An Ultra-High Resolution Map of Dark Matter, with a parenthetical around dark, because the technique measures all mass, visible and invisible. The numbers tell the story. The map covers a field of 0.77 degrees by 0.70 degrees. It achieved an angular resolution of 1.00 arc-minutes, plus or minus 0.01. That is more than twice the resolution of the best previous maps from Hubble. Using JWST's NIR cam in 2 independent filters with a spatial resolution of 0.02 arc-seconds per pixel and approximately 250,000 galaxies contributing to the weak lensing analysis, the team reconstructed the dark matter distribution across the Cosmos Webb field out to a redshift of about 2, meaning they are tracing dark matter structures as they existed 8 to 11 billion years ago. What they found was, in broad strokes, a confirmation of everything that the 2007 map had shown, but in vastly more detail. The filaments are there. The nodes where filaments intersect are there. The voids between them are there. But now, you can also see structures that were invisible before. Small galaxy groups, too faint and too low mass for Hubble or ground-based surveys to detect, sitting along the filaments. Delicate bridges of dark matter connecting clusters. Features as fine as individual dark matter, halos around small clusters. Scognamiglio described it this way. Previously, we were looking at a blurry picture of dark matter. Now we are seeing the invisible scaffolding of the universe in stunning detail. Massey, returning to the imagery he had coined 2 decades earlier, added that the map shows us that dark matter and regular matter have always been in the same place. They grew up together. The plan now is to build a full 3-dimensional version of the map by incorporating photometric redshifts for the background galaxies, slicing the dark matter distribution into layers at different epochs. And the cosmos field itself is being groomed for an even larger role. It will serve as the calibration reference point for 3 massive upcoming surveys. Euclid, the European Space Agency mission that launched in 2023, will eventually survey 14,000 square degrees, over a third of the sky. The Nancy Grace Roman Space Telescope, set to launch later this decade, will cover an area 4,400 times larger than Cosmos Webb, though at lower resolution. And the Rubin Observatory, bearing Vera Rubin's name, will survey 18,000 square degrees over 10 years. All of these surveys will need to benchmark their weak lensing measurements against a field where the answer is already known with exquisite precision. That field is cosmos. So the map is beautiful, the confirmation is robust, and the Lambda CDM model that predicted this cosmic web gets another victory. Dark matter formed the scaffolding. Ordinary matter fell into it. Stars lit up at the densest points. The model works. This should be the end of the story. Everything checks out. The predictions match. The case is closed. But this is where it gets complicated, because the same kinds of measurements that produce this beautiful map, when applied to slightly different questions at slightly different scales, have been returning answers that do not quite agree with each other. And the disagreements, while some of them have recently been explained away as measurement errors, are collectively creating a picture of a model that works spectacularly well in broad strokes, but might be getting the fine print wrong. To understand why this matters, you need to understand what Lambda CDM actually is and what it actually predicts. Because the standard model of cosmology is one of the most successful theoretical frameworks in the history of science, and the tensions it faces now are coming not from its failures, but from its precision. Lambda CDM is built on a deceptively simple foundation. The universe is composed of three major components. Roughly 68.5% of its total mass energy is dark energy, represented by the Greek letter lambda, which drives the accelerating expansion of space. About 26.4% is cold dark matter, which interacts gravitationally but not electromagnetically, and which was moving slowly enough in the early universe, hence cold, to clump together and form the cosmic web. The remaining 4.9% is ordinary baryonic matter, the stuff you and I are made of, along with everything we can see through telescopes: stars, gas, dust, planets, people, all of it. Less than 5% of the total, with just 6 free parameters. This model achieves a level of agreement with observation that borders on absurd. The cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky, has been measured by the Planck satellite from the largest angular scales down to fractions of a degree. Lambda CDM fits this power spectrum, which covers temperature fluctuations spanning several orders of magnitude with sub-percent precision. The angular scale of the acoustic peaks, which encode the size of sound waves in the early universe, is measured to 0.03% accuracy. The number of neutrino species inferred from the CMB is 2.99, plus or minus 0.17. The standard model of particle physics predicts 3.046. That agreement is almost eerie. The model predicts that the sound waves that rang through the hot plasma of the early universe would leave a characteristic imprint on the distribution of galaxies today, a slight excess of galaxy pairs separated by about 150 megaparsecs, roughly 490 million light-years. These are called baryon acoustic oscillations, and they were detected in 2005 at exactly the predicted scale by both the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey. Lambda CDM predicted Big Bang nucleosynthesis would produce specific ratios of hydrogen, helium, deuterium, and lithium, and the observed abundances of the first 3 match across 9 orders of magnitude. The age of the universe derived from the model, 13.797 billion years, plus or minus 23 million, agrees with completely independent estimates from globular cluster ages and white dwarf cooling curves. This is not a model that is failing. This is a model that has been tested against observation after observation after observation for 4 decades and has passed essentially every test. And that is precisely what makes the remaining disagreements so troubling. When a model this successful starts producing answers that do not match, you cannot dismiss the model and you cannot dismiss the data. Something has to give. The sharpest disagreement involves the Hubble constant, the rate at which the universe is expanding, and it is not a small discrepancy. When you use Lambda CDM to extrapolate from the cosmic microwave background, you get an expansion rate of 67.4 kilometers per second per megaparsec, plus or minus 0.5. When you measure the expansion rate directly by building a distance ladder from nearby Cepheid variable stars to Type 1 as supernovae in distant galaxies, you get 73.49 kilometers per second per megaparsec, plus or minus 0.93. The difference is about 9%, and it stands at 5 to 6 standard deviations of significance. The probability of this being a statistical fluke is less than 1 in 3.5 million. For years, critics suggested that the disagreement might be an artifact of how Cepheid stars were measured. In crowded stellar fields, the light from nearby stars can contaminate the measurement, making Cepheids appear brighter or dimmer than they actually are. If the local measurement was biased, the tension would disappear. But the James Webb Space Telescope, with its superior resolution, has now observed the same Cepheids that Hubble measured and found that crowding and blending are not the explanation. The JWST observations ruled out this systematic at 8 sigma of confidence. The local measurement holds, and just to drive the point home, a completely independent method called gravitational time delay lensing, which uses the time delay between multiple images of background quasars lensed by foreground galaxies, measured the Hubble constant at 72.1 kilometers per second per megaparsec from 8 lensed systems in 2025. That is consistent with the local measurement and inconsistent with the CMB prediction. The universe appears to be expanding faster than our best model says it should. And nobody knows why. But the Hubble tension is not the only crack. There is a second disagreement, one that is more directly connected to the dark matter maps we have been discussing, and it involves how clumpy the universe is. The parameter is called S8, and it quantifies the amplitude of matter density fluctuations in the universe today. Think of it this way. The early universe was extraordinarily smooth. The cosmic microwave background shows temperature fluctuations of about 1 part in 100,000, which correspond to equally tiny density variations. Over 13.8 billion years, gravity amplified those tiny seeds into the cosmic web. Regions that were slightly denser than average pulled in more matter, grew denser still, and eventually formed the filaments and clusters we see today. Regions that were slightly less dense than average lost matter to their neighbors and became voids. S8 measures the end result of this process. A higher value means more clumping, more structure, a lumpier universe. A lower value means less clumping, a smoother distribution of matter. Lambda CDM, using the initial conditions measured by Planck in the cosmic microwave background, predicts exactly how much clumping should have occurred by now. And for several years, the weak lensing surveys that directly measure the clumpiness of the late universe were getting a lower number than the model predicted. The Planck prediction for S8 is 0.832, plus or minus 0.013. The Dark Energy Survey's Year 3 analysis, published in 2022, measured 0.759, plus or minus 0.024. The Kilo Degree Survey, or KIDS, in its 2021 analysis, found 0.759 as well, with similar uncertainty. The Subaru Hyper Suprime Cam survey's Year 3 results gave 0.776. Each measurement was individually 2 to 3 standard deviations below the prediction. Collectively, they painted a consistent picture. The late universe is about 8 to 10% less clumpy than Lambda CDM says it should be. If this were real, the implications would be enormous. It would mean that something is suppressing the growth of cosmic structure, preventing dark matter from clumping as efficiently as gravity alone predicts. Several exotic explanations were proposed. Dark matter might interact with neutrinos, creating dark acoustic oscillations that wash out small-scale structure. Dark matter might be slowly decaying, converting a fraction of its mass into invisible radiation. Dark energy might exert friction on dark matter, dragging against its collapse. Any of these would require new fundamental physics beyond Lambda CDM. But here is where the story takes a turn that is less dramatic than the headlines would have you believe, and more important than the drama. The most recent analyses have largely closed the gap. The final Kids Legacy results, published in March of 2025, found S8 equal to 0.815 plus 0.016 minus 0.021. That is consistent with Planck at less than 1 standard deviation. The shift from 0.76 in the earlier analysis to 0.82 in the final version came from improved photometric redshift calibration, extension of the source galaxies to higher redshifts, and more sophisticated modeling of intrinsic alignments, which is the tendency for galaxies that formed in the same gravitational environment to be naturally oriented in similar directions, mimicking the lensing signal. The Hyper-Suprime Cam survey showed a similar shift when its calibration was updated using spectroscopic data from the DESI instrument. S8 moved from 0.769 to 0.805, plus or minus 0.018, consistent with Planck. When you combine all three, Stage 3 weak lensing surveys with their most recent calibrations, the result is S8 equal to 0.813, with uncertainties of about plus or minus 0.01. That is in full agreement with Planck, at roughly 1 standard deviation. The S8 tension, which made headlines from about 2017 to 2024 as evidence that the universe was less clumpy than it should be, was, to a large extent, a measurement, systematic. Better calibration of galaxy distances, better modeling of intrinsic alignments, and extension to higher redshift source galaxies brought the numbers into alignment. The universe is, as far as weak lensing can tell us, about as clumpy as Lambda CDM predicts. That is an important correction to the narrative, and one that a lot of popular science coverage has not caught up with. The dramatic version of this story is that dark matter maps revealed the universe is smoother than expected and our model is broken. The accurate version is that dark matter maps, when measured with sufficient care, show a universe that matches the model to within the uncertainties. The cracks were in the measurements, not in the cosmos. But that is not the end of it, because even as weak lensing surveys have come into alignment with Planck, other probes have not. A galaxy clustering analysis from the BOSS survey found structure growth suppressed at 4.5 standard deviations compared to Lambda CDM predictions. The DESI emission line galaxy survey still shows low values of structure growth at about 3 sigma, and the Hubble tension, which has nothing to do with clumpiness and everything to do with expansion rate, remains stubbornly unresolved at 5 to 6 sigma. The model bends. It has not broken, but the bending is real, and the instruments that will determine whether it snaps or springs back are already in operation. To appreciate what is at stake, it helps to understand just how much work has gone into confirming that the Lambda CDM version of the cosmic web is right. The dark matter maps from weak lensing are observational. They show us what the universe actually looks like. But to test a model, you also need to know what the universe should look like, and generating those predictions requires simulating the entire history of cosmic structure formation from scratch, starting 13.8 billion years ago, with the tiny density fluctuations imprinted in the cosmic microwave background and running gravity forward through all of cosmic time until you reach the present day. The Millennium Simulation, published in 2005 by Volker Springel and the Virgo Consortium, was one of the first to do this convincingly. It tracked roughly 10 billion dark matter particles in a cubic volume about 2 billion light-years on a side, producing 25 terabytes of data and evolutionary histories for approximately 20 million simulated galaxies. The result was a cosmic web that looked almost indistinguishable from the one observed in galaxy surveys. Filaments, nodes, voids, clusters, all in the right places, at the right scales, with the right statistics. Lambda, CDM's hierarchical structure formation, in which small structures form first and merge over time into larger ones, reproduced the observed universe with remarkable fidelity. But the Millennium Simulation included only dark matter and gravity. It did not model the behavior of ordinary matter, the gas and stars and galaxies that actually emit the light we observe. Later simulations addressed this. The illustrious TNG project, running from 2017 to 2019, used a sophisticated moving mesh hydrodynamics code called ARIPO to simulate dark matter, gas, stars, and supermassive black holes simultaneously. Its 3 flagship simulations spanned different volumes and resolutions, and one of its most important findings was that the energetic feedback from supernovae and active galactic nuclei, the jets of energy that supermassive black holes blast into their surroundings, can suppress the total matter power spectrum by roughly 20% at small scales. That is a significant number because it means that the clumpiness of the universe at small scales is not determined by dark matter alone. The behavior of ordinary matter, and specifically the explosive feedback from stars and black holes, affects the result. This matters enormously for the S8 story. If baryonic feedback suppresses small-scale structure by 20%, and your weak lensing analysis does not account for that suppression, you will measure a lower S8 than Lambda CDM predicts from the CMB. Not because the model is wrong, but because you are comparing the wrong prediction to the data. Several recent papers have argued that baryonic feedback is the leading mundane explanation for at least part of the S8 discrepancy, particularly at the smaller angular scales where the effect is strongest. But there is a tension within this explanation that has not been fully resolved. The amount of feedback needed to explain the S8 discrepancy is at the high end of what simulations consider plausible. If you need 20% suppression and your simulations produce 10 to 20%, depending on the feedback model, you are relying on the most aggressive end of the theoretical range. Some physicists are comfortable with that, others are not. And even if baryonic feedback explains S8, it does nothing for the Hubble tension. These are 2 different cracks, requiring 2 different explanations. And the Hubble tension is the bigger of the 2 by a wide margin. Meanwhile, the theorists have not been idle. In January of 2026, the same month that the Cosmos Webb Dark Matter Map was published, a team led by Lemaître published a paper in Nature Astronomy proposing a specific new interaction between dark matter and neutrinos. Their model introduces a scattering interaction between dark matter particles and neutrinos with an interaction strength of about 10 to the -4, which would create what they call dark acoustic oscillations, analogous to the regular acoustic oscillations that ring through the early universe's plasma, but operating in the dark sector. These oscillations would suppress small-scale structure formation, naturally producing a lower S8 when they fit their model to the combined data from Planck, baryon acoustic oscillations, the Atacama Cosmology Telescope, and the Dark Energy Survey. They find a roughly 3 sigma preference for non-zero dark matter neutrino interactions over the standard Lambda CDM model. 3 sigma is interesting. It is the level where physicists start paying attention, but not the level where they start believing. The particle physics standard for discovery is 5 sigma, and cosmology has been burned by 3 sigma signals before. But the paper is part of a broader trend in which the theoretical community is actively exploring what lies beyond Lambda CDM, not because the model has failed, but because the data are now precise enough to see where it might be wrong. Other proposals include decaying dark matter, in which a small fraction of dark matter particles decay over cosmic time with a half-life of about 55 billion years, transferring about 0.7% of their rest mass energy into invisible radiation. There are models of dark matter interacting with dark energy, creating a drag force between the 2 dominant components of the universe that would slow down structure growth during the recent epoch when dark energy began to dominate. Warm dark matter models propose that a fraction of the dark matter was produced with higher velocities in the early universe, smoothing out small-scale structure. Self-interacting dark matter models address a different set of problems, primarily at the scale of individual galaxies, where Lambda CDM predicts cuspy density profiles that are not always observed. None of these models have been confirmed. All of them make specific predictions that will be tested by the next generation of surveys. And the next generation of surveys is not a distant promise. It is already collecting data. There is something almost poetic about where we stand right now. 93 years after Fritz Zwicky looked at a handful of galaxy velocities and realized the universe was mostly invisible, we have mapped that invisible matter with higher precision than anyone in 1933 could have imagined. The scaffolding is real. The web is there. Dark matter built the architecture of the cosmos, and galaxies formed along its bones. But the same precision that confirmed the scaffolding has revealed that the fine structure of the model might not be right. We built a framework that works beautifully at the larger scales. The cosmic microwave background, the baryon acoustic oscillations, the cosmic web. Now we are pushing into the details, and some of the details are pushing back. The question that opened this story remains open. Do we actually understand what holds the universe together? The scaffolding says yes. The Hubble tension says maybe not. The S8 tension said no for 7 years, and then, upon more careful measurement, said actually, we might have been measuring wrong, and new surveys are about to test the model with a precision that will leave nowhere to hide. The next part of this story involves the telescopes that are about to deliver that verdict. The experiments that have spent years trying to catch a dark matter particle in a vat of liquid xenon deep underground, and a Belgian priest who figured out the expanding universe before anyone else and spent decades being told he was wrong. Because the human thread running through all of this, from Zwicky's rage to Rubin's quiet persistence, to a Belgian priest whose faith and physics pointed in the same direction, is as essential to understanding dark matter as any equation or observation. The people who chase the invisible have always been the ones the establishment found hardest to see. Georges-Henri Joseph Edouard Lemaître was born on July 17, 1894, in Charleroi, Belgium, the eldest of 4 children. He studied civil engineering at the Catholic University of Leuven, and when the First World War broke out, he volunteered for the Belgian army and served as an artillery officer. He saw combat at the Battle of the Yser. He was decorated for bravery. And when the war ended, he did something that surprised the people who knew him. He entered a seminary, studied theology, and was ordained as a Catholic priest in 1923. He also, simultaneously, earned a doctorate in mathematics. This combination, priest and physicist, has been used in the popular accounts to paint Lemaître as some kind of paradox. It was not a paradox to him. He kept the two domains rigorously separate. When Pope Pius XII attempted to use Lemaître's cosmological work as proof of creation in a 1951 address, Lemaître was reportedly horrified and worked behind the scenes to ensure the Vatican did not repeat the claim. Science and faith, in his view, answered different questions. He was not using one to validate the other. What he was doing in the 1920s was solving Einstein's field equations of general relativity. And in 1927, 2 years before Edwin Hubble published the observational paper that would make the expanding universe famous, Lemaître independently derived the solution that showed the universe must be expanding. His paper, published in the Annales de la Société Scientifique de Bruxelles, was titled A Homogeneous Universe of Constant Mass and Growing Radius, accounting for the radial velocity of extragalactic nebulae. It was written in French and published in a Belgian journal that almost nobody outside of Belgium read. Lemaître not only derived the expansion solution, but also used Hubble's own observational data, which had been published separately, to estimate the rate of expansion. He arrived at a value of about 625 kilometers per second per megaparsec, which is wildly too high by modern standards, but was derived from the same data that Hubble would use 2 years later. The priority question here is worth pausing on, because it reveals something important about how scientific credit works, or fails to work. When Arthur Eddington arranged for Lemaître's paper to be translated into English and published in the monthly notices of the Royal Astronomical Society in 1931, the translation omitted the paragraph in which Lemaître had estimated the expansion rate. For decades, historians assumed Eddington had censored it. It was not until 2011 that Mario Livio, working at the Space Telescope Science Institute, found evidence that Lemaître himself had removed the paragraph from the translation, apparently because by that time, Hubble's more precise determination had superseded his own, and he did not consider the cruder estimate worth preserving. The irony is exquisite. Lemaître's modesty erased the evidence that he had gotten there first. It was not until 2018 that the International Astronomical Union voted to rename the Hubble law as the Hubble-Lemaître law, formally acknowledging a priority that the historical record had supported for decades, but that the physics community had been slow to recognize. By then, Lemaître had been dead for over 50 years. When Lemaître presented his results to Einstein at the 1927 Solvay conference in Brussels, Einstein's response was blunt and dismissive. "Your calculations are correct," he told Lemaître, "but your physics is abominable." Einstein was at the time committed to a static, eternal universe. He had introduced the cosmological constant, Lambda, into his field equations specifically to prevent them from predicting expansion or contraction. The idea that the universe was growing struck him as not just wrong, but distasteful. Lemaître was polite about it. He went back to Belgium. He continued working. And in 1931, he took the expanding universe to its logical conclusion. If the universe is expanding now, and if you run the expansion backward in time, everything converges to a single point. Lemaître proposed that the universe began as a single initial quantum, which he called the primeval atom, a state of maximum density from which all of space and matter expanded. This was, for all practical purposes, the first scientific model of what we now call the Big Bang. The name Big Bang was actually coined as a mockery. Fred Hoyle, the British astronomer who championed the rival steady-state theory, used the phrase during a 1949 BBC radio lecture to ridicule the idea of a singular origin. The name stuck. Hoyle later insisted he had not meant it as a joke, but the historical context suggests otherwise. Lemaître went further. In 1934, he published a paper reinterpreting Einstein's cosmological constant, not as a mathematical fudge factor, but as a physical property of the vacuum. He was the first person to suggest that empty space itself might contain energy, and he estimated that this vacuum energy would correspond to a cosmic background temperature of a few degrees above absolute zero. 3 decades later, Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation at a temperature of 2.7 Kelvin. Lemaître, by then elderly and nearly blind, learned of the discovery shortly before his death on June 20th, 1966. According to those who were with him, he said simply, "I'm glad now. We have the proof. The lambda in lambda, CDM, the cosmological constant that represents dark energy, is Lemaître's direct intellectual legacy." In 2018, the International Astronomical Union voted to rename the Hubble law as the Hubble-Lemaître law, formally acknowledging what the historical record had shown for decades. Lemaître got there first. He just published in the wrong journal, in the wrong language, at the wrong time. This is the thread that connects all 3 biographical stories in this documentary. Zwicky published his dark matter result and was ignored because he was personally impossible. Rubin proved dark matter was everywhere and was excluded from the institutions that should have celebrated her. Lemaître derived the expanding universe before anyone else and was dismissed because Einstein, the most famous physicist alive, told him his physics was abominable. In each case, the science was right, the establishment was wrong, and the delay between discovery and acceptance was measured not in months, but in decades. You might be tempted to draw a clean moral from this, something about how outsiders see the truth before insiders, but the real lesson is more uncomfortable than that. The establishment was not stupid in any of these cases. Zwicky's factor of 400 was actually wrong, even if his underlying insight was right. Rubin's early thesis on galaxy distributions was genuinely ahead of the available data. Lemaître's expanding universe was published in an obscure journal and required accepting a radical change to the prevailing cosmological framework. In each case, there were defensible reasons for skepticism, and in each case, those reasons were amplified by bias, by personality conflict, by institutional exclusion. The people who proved that 95% of the universe is invisible or unexplained were themselves, to varying degrees, invisible to the people who controlled the field. That is not a coincidence. It is a pattern, and it persists. The reason we know dark matter exists is that we can see what it does. Galaxies rotate too fast. Galaxy clusters are too hot. Light bends where nothing visible sits. The cosmic web has the exact structure that invisible mass would produce. The evidence is overwhelming, and it all comes from gravity. But knowing that dark matter exists gravitationally is different from knowing what it is. For that, you would need to detect it directly. You would need a dark matter particle to interact with ordinary matter in some way other than gravity, at a rate high enough to register in a detector, and at an energy low enough that the interaction does not destroy the detector itself. For decades, the leading candidate has been a class of hypothetical particles called WIMPs, weakly interacting massive particles. WIMPs are attractive because they arise naturally in many extensions of the standard model of particle physics, particularly in supersymmetric theories. If WIMPs have masses in the range of about 10 to 1,000 times the mass of the proton, and if they interact with ordinary matter through the weak nuclear force, then the conditions of the early universe would have produced them in exactly the right abundance to account for the observed dark matter density. This coincidence is called the WIMP miracle, and it motivated 3 decades of experimental searches. The basic principle of direct detection is simple. Take a large volume of extremely pure material, typically liquid xenon, cool it to cryogenic temperatures, surround it with shielding to block cosmic rays and natural radioactivity. Bury it deep underground, where rock absorbs most of the remaining background radiation, and wait. If a WIMP from the galaxy's dark matter halo drifts through the detector and happens to bounce off a xenon nucleus, the recall produces a tiny flash of light and a small pulse of electric charge. The detector records both signals, and the ratio between them distinguishes a potential dark matter interaction from a background event. The world's most sensitive experiment of this type is called Lux Zeppelin, or LZ, and it is located 1 mile underground at the Sanford Underground Research Facility in Lead, South Dakota, in the same cavern that once housed the Home State gold mine. There is a symmetry here that physicists appreciate. The Home State mine was where Raymond Davis Jr. built his famous neutrino detector in the 1960s, the chlorine tank experiment that first detected solar neutrinos and helped establish that the sun runs on nuclear fusion. 6 decades later, the same underground space is being used to search for a different ghostly particle. The LZ detector contains 10 tons of liquid xenon in an active target surrounded by layers of ultra-pure titanium, acrylic, and gadolinium-loaded liquid scintillator. The xenon is purified to a level where the total background radioactivity from Krypton 85 is less than 0.3 microbecquerels per kilogram, roughly 10 million times less contamination than ordinary commercial xenon. The entire apparatus is immersed in a tank of ultra-pure water that serves as both shielding and a muon veto, catching the rare cosmic ray muons that penetrate the mile of rock above. When a particle interacts with a xenon nucleus, two signals are produced almost simultaneously. First, the recoil creates a flash of scintillation light in the liquid, detected by arrays of photomultiplier tubes at the top and bottom of the detector. Second, the recoil liberates electrons from the xenon atoms, and these electrons drift upward under an applied electric field to the liquid-gas boundary at the top of the detector, where they produce a second flash of light. The ratio of these two signals, the prompt scintillation and the delayed electroluminescence, allows physicists to distinguish nuclear recoils from electron recoils, which is essential because most background events are electron interactions from gamma rays and beta decays, not nuclear collisions. The LZ team's latest results, reported in December of 2025, are based on 417 live days of data, the largest dataset ever collected by a dark matter direct detection experiment. The result was unambiguous. No WIMPs were detected. LZ achieved the world's leading sensitivity for dark matter particles with masses above 5 billion electron volts, pushing the upper limit on the interaction strength between dark matter and ordinary matter to the lowest values ever recorded. Whatever dark matter is, it interacts with normal matter either extremely rarely or not at all through the weak force. But the LZ result contained a remarkable silver lining. In the process of searching for dark matter, the detector made the first observation of solar neutrinos through a process called coherent elastic neutrino nucleus scattering, or CEVNS. Neutrinos from the Sun, streaming through the rock and into the detector, were bouncing off xenon nuclei in the same way that dark matter was supposed to. The detection was significant at 4.5 standard deviations. This matters because it confirms that direct detection experiments have reached what physicists call the neutrino floor, or more precisely, the neutrino fog. Below a certain sensitivity threshold, neutrino interactions become an irreducible background that mimics dark matter signals. Future experiments will still be able to search for dark matter below this floor, but they will need to develop new techniques to distinguish genuine dark matter events from neutrino scattering. The LZ experiment has effectively explored the most optimistic corner of WIMP parameter space and found nothing. The easy version of the WIMP miracle appears to be ruled out. That does not mean WIMPs are dead. There are regions of parameter space, particularly at lower masses, that LZ and its predecessors have not yet explored. And WIMPs are not the only candidate. Axions, originally proposed to solve a problem in quantum chromodynamics having nothing to do with dark matter, could be produced in the early universe at the right abundance and with the right properties. The ADMX experiment at the University of Washington is searching for axion dark matter using a high-sensitivity microwave cavity, and the CERN Axion Solar Telescope, or CAST, searched for axions produced in the Sun. Neither has found anything yet, but the search space is vast, and the experiments are still in early phases relative to their ultimate sensitivity. There is also a provocative claim from November of 2025 that deserves mention. though it comes with heavy caveats. Tomonori Totani at the University of Tokyo reported finding a 20 gigaelectron-volt halo-shaped gamma-ray excess in 15 years of data from NASA's Fermi Gamma-Ray Space Telescope. The excess is consistent with the annihilation of dark matter particles with a mass of about 500 times the proton mass, which would produce gamma rays as their annihilation products. If confirmed, this would be a monumental discovery, the first detection of dark matter through something other than gravity. However, the experts are skeptical, and for good reason. Jan Conrad at Stockholm University noted that it is notoriously difficult to make these claims with Fermi data. The galactic center is a complex environment, filled with pulsars, molecular clouds, and diffuse emission that are extremely difficult to model and subtract. Similar excess claims have been circulating since 2009. None have been confirmed. The history of dark matter detection is littered with tantalizing hints that evaporated under scrutiny. This may join them. So the direct detection picture, as of early 2026, is this. The most sensitive experiments ever built have found nothing. The neutrino floor has been reached, making future searches harder. The WIMP miracle, in its simplest and most compelling form, appears to be fading, and the only positive claim of a detection signal is unconfirmed and viewed with significant skepticism by the broader community. We know dark matter is there. We can map it with exquisite precision across billions of light years, but we have never caught a single particle of it. Whatever it is, it does not want to be found. Which brings us back to the telescopes, because if we cannot catch dark matter in a laboratory, the next best thing is to measure its effects on the universe with such extraordinary precision that the measurements themselves constrain what dark matter can and cannot be. The European Space Agency's Euclid mission launched on July 1st, 2023, and began its science survey on February 14th, 2024. Euclid carries a 1.2-meter telescope and two instruments, a visible light imager and a near-infrared spectrometer photometer. It is designed to do one thing extremely well: map the geometry and growth of cosmic structure across more than a third of the sky. Euclid's Quick Data Release 1, published in March of 2025, covered 63 square degrees and delivered results that preview the scale of what is coming. The survey catalogued 26 million galaxies, with the most distant sitting 10.5 billion light-years away. It classified over 380,000 galaxy morphologies, and it discovered more than 500 new gravitational lens candidates, compared to only about 150 that were previously known from space-based telescopes. Euclid's images are 4 times sharper than those from ground-based observatories. When the full weak lensing cosmological constraints arrive with Data Release 1, expected in October of 2026, they will be the most precise measurement of the matter distribution in the late universe ever produced from a single survey. By the time Euclid completes its mission, it will have surveyed 14,000 square degrees, measuring the shapes of roughly 1.5 billion galaxies. That is an order of magnitude more than any Stage 3 survey. And Euclid is not working alone. The Vera Rubin Observatory, with its 8.4-meter mirror and 3,200 megapixel camera, will survey 18,000 square degrees of the southern sky over 10 years, providing complementary ground-based weak lensing measurements. The Nancy Grace Roman Space Telescope, carrying a 2.4-meter mirror with a field of view 100 times larger than Hubble's, will map dark matter across an area 4,400 times larger than Cosmos Webb. Together, these three observatories, plus JWST's ultra-deep calibration fields, will constrain Lambda CDM with a precision that makes everything before them look like squinting through a keyhole. The DESI experiment, the Dark Energy Spectroscopic Instrument, mounted on the 4-meter Mail telescope at Kitt Peak in Arizona, is already providing a different kind of data. DESI is measuring the redshifts of tens of millions of galaxies and quasars, constructing a 3-dimensional map of the universe that traces the baryon acoustic oscillation signal at multiple epochs. Its Data Release 2, published in March of 2025, used 11 million galaxies to measure the expansion history of the universe from redshift 0.1 to redshift 4.2, covering roughly 12 billion years of cosmic time. The results were provocative. When DESI combined its baryon acoustic oscillation measurements with supernova distance data, the joint analysis excluded Lambda CDM at somewhere between 2.8 and 4.2 standard deviations, depending on which supernova dataset was used. The data preferred a model in which dark energy is not constant, but evolving, weakening over time. If Lambda, the cosmological constant that Lemaître first gave physical meaning to in 1934, is not actually constant, then the simplest version of Lambda CDM is wrong, and the dark energy sector of the model needs modification. But there are important caveats. DESI's baryon acoustic oscillation data alone, without supernovae, remains consistent with Lambda CDM. The tension appears only in the combination, and the significance depends sensitively on how the supernova data are calibrated and which sample is used. Some analysts argue that the apparent evolution of dark energy could be an artifact of systematic errors in the supernova distances. Others argue that the signal is robust and the universe is telling us something real. There is yet another tension that deserves mention here, one that briefly looked like it might topple Lambda CDM entirely, but has since been substantially walked back. When JWST's first deep field images arrived in the summer of 2022, astronomers were stunned to find what appeared to be massive, mature galaxies at redshifts of 7 to 14, meaning they existed when the universe was less than 700 million years old. Some of these galaxies appeared to contain 10 billion solar masses of stars or more. In 2023, Boyle and Colchin published an analysis in Nature Astronomy showing that the most massive candidates required baryon-to-star conversion efficiencies approaching 100%, meaning essentially every atom of hydrogen and helium in these galaxies would have had to convert into stars. Typical galaxies manage about 5 to 10%. If the masses were real, Lambda CDM's predictions for early structure formation were in serious trouble. But the masses turned out to be significantly overestimated for multiple reasons that became clear over the following 2 years. Many of the reddest and most massive-looking objects turned out to be active galactic nuclei, compact sources where a supermassive black hole's accretion disk was mimicking the colors of a massive galaxy. Early JWST photometric calibrations were slightly off, inflating brightnesses, and superheated dust around these young galaxies made them appear more luminous than their stellar mass warranted. By 2024, multiple independent groups had revised the mass estimates downward. Star formation efficiency at high redshift was indeed higher than expected, which was interesting and required some adjustments to galaxy formation models. But Lambda CDM itself was not broken. The predicted dark matter halos were forming on schedule. The galaxies inside them were just slightly better at making stars than astrophysicists had assumed. This episode is instructive. When JWST first found those galaxies, the headlines screamed that the Big Bang model was in crisis. Within 2 years, careful analysis showed that the observations were perfectly compatible with the standard model once calibration and identification errors were corrected. It is a reminder that tensions in cosmology need time to mature before you can tell whether they are real cracks or measurement artifacts. The S8 tension turned out to be mostly measurement. The massive galaxy tension turned out to be mostly measurement. The Hubble tension has survived every attempt to explain it as measurement. The DESI dark energy hint is too young to know. This is the kind of uncertainty that a documentary can present honestly without needing to resolve. The answer is not yet known. Multiple independent analyses disagree. The data are being scrutinized by hundreds of physicists around the world. And the next round of DESI results, along with Euclid's first cosmological constraints, will provide a much clearer picture within the next year or two. What is not uncertain is that the stakes are real. If dark energy is evolving, the implications cascade through all of cosmology. The fate of the universe changes. Lambda CDM's 6-parameter economy breaks. The cosmological constant, Einstein's biggest blunder, which Lemaître rescued and reinterpreted, which became the backbone of the standard model, would need to be replaced by something more complex and more interesting. Let's stop for a moment and try to make the numbers in this story feel real. Because the problem with cosmology is that the scales are so absurd that the human brain has no intuitive access to them. And if the numbers remain abstract, the story loses its weight. Start with the composition of the universe. For every kilogram of matter you can see, every star and planet and gas cloud, every atom in your body and every grain of sand on Earth, there are roughly 5 kilograms of dark matter. If the mass of all ordinary matter in the observable universe were represented by a single human being, the dark matter would be a family of 5 standing behind them, completely invisible, exerting gravitational influence on everything, but never touching anything, never emitting a single photon of light. Now zoom out. The Milky Way, our galaxy, contains roughly 300 billion stars. The total baryonic mass, all the gas and dust and stars combined, is about 33 billion solar masses. But the dark matter halo surrounding our galaxy has a mass of approximately 1 trillion solar masses. It extends to a radius of roughly 950,000 light-years from the galactic center, more than 4 times the distance to the large Magellanic Cloud. Our galaxy, the thing we see when we look up at the night sky, the band of light that gave the Milky Way its name, is about 3% of the total mass of the system it inhabits. The other 97% is dark matter. If you could somehow see dark matter and you stepped outside on a clear night, the Milky Way would not be a thin band of light across the sky. It would be a faint glow embedded in an enormous, roughly spherical fog that extends 4 times further than the galaxy itself, in every direction. The stars would be a thin disk of bright specks inside a halo so vast that the visible galaxy is just a small, luminous core. Now scale up further. The cosmic web, the network of dark matter filaments that the Cosmos Web Map revealed, operates at scales that make galaxies look like dust motes. Individual filaments stretch 50 to 80 megaparsecs in length, which translates to roughly 160 to 260 million light-years. The longest known filaments exceed 400 megaparsecs, over 1 billion light-years from end to end. If you could somehow travel along one of these filaments at the speed of light, the journey would take longer than the age of the earliest complex multicellular organisms on Earth. 1 billion years just to traverse a single strand of the web. Between the filaments are voids, regions of space that are nearly empty. The Boots void, discovered in 1981, is about 330 million light-years across. It contains roughly 60 known galaxies. For comparison, a volume of that size in a typical part of the universe would contain thousands. Imagine a city the size of Los Angeles, with 60 people in it. That is the Bootes void. And the galaxy, clusters that sit at the intersections of the filaments, the dense nodes where dark matter has accumulated over billions of years, are the most massive, gravitationally bound structures in the universe. The Coma cluster, the same one that Zwicky studied in 1933, has a modern total mass estimate of about 1.4 times 10 to the 15th solar masses. To put that in perspective, if every human being who has ever lived were given their own sun, every person who ever breathed, estimated at roughly 110 billion people across all of human history, you would need to repeat that exercise about 13,000 times to account for the mass of the Coma cluster. And 85 to 90% of that mass is dark matter. These numbers exist at the boundary of what human cognition can process, but they are not abstractions. The Cosmos Web Map is a photograph of this structure, seen through the gravitational distortion it imposes on background light. The filaments are real. The voids are real. The nodes are real. And the fact that we can map them at all from a telescope orbiting the Sun 1.5 million kilometers from Earth, measuring 1% distortions in the shapes of galaxies billions of light-years away, is among the most remarkable technical achievements our species has ever managed. Consider, for a moment, the detection chain involved. A galaxy billions of light-years away emits light. That light travels for billions of years across expanding space. Somewhere along the way, it passes through a region where dark matter has accumulated, and the dark matter's gravity bends its path ever so slightly, distorting the galaxy's apparent shape by about 1%. The light continues traveling, eventually reaching the James Webb Space Telescope at the second Lagrange point, 1.5 million kilometers from Earth, where a 6.5-meter gold-plated mirror collects it and focuses it onto a near-infrared detector, cooled to minus 233 degrees Celsius. The detector records the photon positions with a resolution of 0.02 arc-seconds per pixel. Software running on computers in Baltimore, Maryland, measures the ellipticity of that galaxy image, subtracts the distortion introduced by the telescope's own optics, corrects for the slight blurring caused by the finite size of the mirror, estimates the galaxy's distance from its colors, and combines that measurement with hundreds of thousands of similar measurements from other galaxies in the same patch of sky. The aggregate signal, after all corrections and all averaging, reveals the mass distribution of the foreground dark matter. Every single step in that chain operates at the edge of what is technically possible. The mirror has to be perfect to within nanometers. The detector has to be cold enough that its own thermal radiation does not swamp the signal. The software has to model the point spread function of the telescope to a fraction of a % accuracy. The photometric redshifts have to be calibrated against spectroscopic surveys that themselves required years of telescope time to produce. A failure at any point in the chain would produce a map that looks like noise, that the map instead shows coherent filaments and nodes and voids matching the predictions of theoretical cosmology, is not just a scientific result. It is a triumph of engineering, computation, and international cooperation operating at a scale that is, in its own way, as awe-inspiring as the cosmic structures it reveals. And yet the map is also, in another sense, humbling. It shows us the skeleton of the universe, the invisible framework on which everything we can see was built. But it does not tell us what the bones are made of. It does not explain why the expansion rate measured locally disagrees with the one predicted from the early universe. And it does not answer the question that the DESI data have begun to raise. Whether the dark energy that dominates the universe, the 68.5% that is not dark matter and not ordinary matter and not radiation, might be changing over time. If dark energy is evolving, the consequences ripple through everything. A cosmological constant, by definition, does not change. It is a property of the vacuum, fixed for all time. The fate of the universe under a cosmological constant is well understood. Space continues to expand at an accelerating rate. Galaxies outside our local group recede beyond the observable horizon one by one. The night sky slowly empties over hundreds of billions of years, and the universe ends in a cold, dark, infinitely diffuse state, sometimes called the heat death. But if dark energy is not constant, if it is a dynamical field that can strengthen or weaken over cosmic time, then the fate of the universe is not fixed. A dark energy that strengthens could lead to a big rip, in which the expansion of space eventually overcomes every force in nature, tearing apart galaxy clusters, then galaxies, then solar systems, then atoms, in a final catastrophic inflation. A dark energy that weakens could eventually reverse, leading to a recollapse and a big crunch. Or dark energy could oscillate, producing cycles of expansion and contraction on timescales vastly longer than the current age of the universe. None of these scenarios are predictions from current data. They are possibilities that become live if Lambda turns out to be a variable. The DESI hint at 2.8 to 4.2 sigma, depending on the supernova sample, is the first empirical indication that Lambda might not be constant. It is not definitive. It might not survive the next round of data. But the fact that it exists at all, from a survey measuring millions of galaxies across 12 billion years of cosmic time, is enough to make cosmologists take seriously the idea that the simplest version of their model might need modification. This is why the Cosmos Web Map and the DESI results, both published in the same period, together represent something more than individual discoveries. They are the opening act of an era in which the precision of measurement has caught up to the precision of the model, and the model is being tested in ways it has never been tested before. There is a common misconception about this topic that is worth addressing, and it connects directly to the question we have been circling throughout this entire story. You hear it constantly in popular science coverage. We don't know what dark matter is. The implication being that because we have not caught a particle of it in a detector, and because it does not appear in the standard model of particle physics, our knowledge of dark matter is somehow shallow or provisional, as if the whole thing might turn out to be a mistake. That framing is deeply misleading. We know an enormous amount about dark matter. We know how much of it there is, both in the universe as a whole and in individual structures from galaxy halos to clusters. We know its spatial distribution at multiple epochs of cosmic history, from the cosmic microwave background at a redshift of about 1080 to the local universe today. We know it is cold, meaning it was moving slowly enough in the early universe to clump gravitationally and form the seeds of structure. We know it is collisionless because the bullet cluster showed it passing through a cluster collision without interacting. We know it is stable on cosmological timescales because the abundance inferred from the CMB 13.8 billion years ago is consistent with the abundance measured today, give or take. We know it does not interact with light, or it would not be dark. We know it does not interact with itself strongly, or the dark matter halos around galaxies would be rounder and denser at the center than they are. This is not a vague outline. This is a detailed behavioral profile of a substance that constitutes 85% of all matter, built from independent lines of evidence that all converge on the same picture. The Planck satellite's measurement of the CMB power spectrum alone constrains the dark matter density to 4 significant figures. The dark matter fraction in galaxy clusters, measured independently through X-ray observations and weak lensing, agrees with the CMB value. The primordial abundance of deuterium, created in the first few minutes of the Big Bang and exquisitely sensitive to the baryon to photon ratio, independently confirms how much baryonic matter exists, and therefore, by subtraction, how much dark matter there must be. These are not rough guesses. They are precision measurements, cross-checked against each other. And they agree. What we do not know is what fundamental particle it is made of, and how to produce or detect it in a laboratory. That is a significant gap, but it is a gap in our particle physics understanding, not in our cosmological understanding. The gravitational behavior of dark matter is extraordinarily well characterized. The particle identity is the remaining mystery. The distinction matters because it changes the character of the central question. The question is not, does dark matter exist, which was settled decades ago. And it is not, what is dark matter, in the sense of a blank void of ignorance. It is something more specific and more interesting, given everything we know about how dark matter behaves gravitationally, and given the increasingly precise maps we are now able to produce. Does the model we have built to describe all of this, Lambda CDM with its 6 parameters and its cold, collisionless dark matter, actually capture the full picture? Or is there something in the behavior of dark matter, in its interactions, in its relationship with dark energy, in its fine-scale distribution, that our current model misses? That is the question the Cosmos Web Map helps to answer. That is the question Euclid and Rubin and Roman will attack. That is the question the Hubble tension and the DESI results are probing from different angles. And that is the question that, as of right now, genuinely does not have a settled answer. The model works spectacularly well at the larger scales. The cosmic web is there. The CMB is matched. The baryon acoustic oscillations ring at the right frequency. But when you push into the fine details, the expansion rate measured locally versus the one predicted from the early universe, the growth of structure as traced by different methods, the possible evolution of dark energy, the model starts to strain. Not break, strain. The historical parallel that fits best is not Ptolemaic astronomy collapsing under the weight of epicycles. Lambda CDM is nothing like the Ptolemaic model. It has 6 parameters, not dozens. Its predictions are precise, not ad hoc. The better parallel is the transition from Newtonian mechanics to general relativity. Newton's theory worked brilliantly for over 2 centuries. It sent spacecraft to the moon. It is still used for most engineering applications today. But when measurements became precise enough, particularly the precession of Mercury's orbit, it became clear that Newton's framework was an approximation of something deeper. The theory was not wrong. It was incomplete. Lambda CDM may be in the same position. Not wrong, but potentially the leading order approximation of a richer theory that accounts for whatever is producing the Hubble tension, whatever is hinted at in the DESI data, whatever dark matter actually is at the particle level. The next generation of surveys will not just test Lambda CDM, they will probe whether the model's extraordinary success at large scales extends all the way down, or whether there is a scale or an epoch or a process where it starts to deviate. The community is genuinely divided on how to interpret where things stand. Dan Skolnick, one of the leading supernova cosmologists, declared at the American Astronomical Society meeting in January of 2025 that the Hubble tension constitutes a crisis. Ethan Siegel, the astrophysicist and science communicator, pushed back. The consensus picture is not so easy to overthrow, he argued, pointing to Lambda CDM's extraordinary track record. Willem Elbers, working on the DESI survey, offered perhaps the most measured assessment. As our data are getting more and more precise, we are finding potential cracks in the model and realizing we may need something new. The word crisis does a lot of work in that debate, and it is worth being honest about what it means and what it does not. A crisis in physics is not a model producing wrong answers everywhere. It is a model producing answers so precise that the remaining disagreements, even small ones, become impossible to ignore. Lambda CDM is in crisis, the way a straight A student who gets a B+ is in crisis. The performance is still extraordinary, but the B+ needs an explanation because the whole identity of the model rests on its ability to get A's. The lithium problem, incidentally, has been there for decades, and nobody calls it a crisis, even though Big Bang nucleosynthesis predicts 2 to 4 times more lithium-7 than is observed. The discrepancy is large, but it affects one element in one prediction, and the other nucleosynthesis predictions are so good that physicists are content to blame astrophysical processes, stellar depletion of lithium, rather than fundamental physics. The Hubble tension is different because it affects something much more fundamental, the expansion rate of the universe itself, and because it has resisted every attempt to blame it on measurement error. Whether the word crisis is appropriate may depend on your temperament more than on the data. But the data are clear. Lambda CDM works far better than it has any right to, and there are specific, well-measured places where it does not work quite well enough. The next few years will determine which of those places are measurement issues and which are nature trying to tell us something. We are approaching the end of this story, and it is worth returning to the three people who, more than anyone, built the framework we are now testing. Fritz Zwicky died in 1974, 6 days before his 76th birthday. Having been largely ostracized by the community, he spent 50 years trying to impress. His dark matter calculation was off by nearly 2 orders of magnitude. But the insight was right. The universe is mostly invisible. He predicted supernovae, neutron stars, gravitational lensing, and the existence of a major new component of the cosmos. All confirmed, all posthumously. Vera Rubin died on Christmas Day, 2016, after a career spent being excluded from the instruments and institutions that her discoveries ultimately made essential. Her rotation curves are still the bedrock of dark matter evidence at the galactic scale. The observatory that bears her name is about to conduct the largest sky survey in history, doing what she did for 200 galaxies across 18,000 square degrees of sky. Georges Lemaître died on June 20th, 1966, 2 weeks after learning that the cosmic microwave background had been detected, confirming the expanding universe he had proposed 35 years earlier over Einstein's objections. The lambda he gave physical meaning to now anchors the name of the standard model itself. These 3 stories share something beyond their scientific content. In each case, the person saw something real and was told, through channels ranging from professional dismissal to institutional exclusion to direct personal insult, that they were wrong. And in each case, the universe proved them right on a timescale that stretched beyond their ability to enjoy it. Zwicky never saw dark matter accepted. Rubin never received the Nobel. Lemaître died just as his cosmology became orthodoxy. The JWST dark matter map, published in January 2026, is, in a very real sense, their monument. It is the scaffolding that Zwicky glimpsed in the velocities of 7 galaxies. It is the invisible halos that Rubin traced in the flat rotation curves of spiral after spiral. It is the expanding cosmic web that grows from the primeval atom that Lemaître proposed when Einstein told him his physics was abominable. And here is the part that I think would have pleased all 3 of them. The map is beautiful. It confirms what they predicted. And it is not enough, because the same instruments that validated their insights have pushed measurement, precision to the point where new questions are emerging. Questions about whether the expansion rate is really constant. Questions about whether dark energy evolves. Questions about what dark matter is at the particle level and whether its behavior at small scales matches what Lambda CDM predicts. Questions that could not have been asked until the measurements became this precise. Zwicky would have railed against anyone who claimed the questions were settled. Rubin would have quietly pointed out that the data will tell you if you let it. Lemaître would have noted, perhaps with a slight smile, that the universe has always been more imaginative than the people trying to describe it. The central question of this documentary remains open. We mapped the invisible scaffolding with the sharpest instrument ever built and found exactly what we expected. But the same era of precision that produced that map is revealing tensions in the model that predicted it, tensions that range from interesting to severe, and that will be tested over the next few years by surveys of a scale and sensitivity that have no precedent in the history of astronomy. 93 years after Fritz Zwicky first wrote the words dunkle Materie, we can see its architecture stretching across billions of light years. We can measure its mass in individual galaxy halos. We can watch its filaments grow over cosmic time. We know more about the invisible universe than any previous generation could have imagined. And we still cannot tell you what it is made of. We still cannot explain why the universe is expanding at two different speeds. We still do not know whether the cosmological constant is actually constant. The scaffolding is real. The questions are open, and the instruments that will answer them or reveal even deeper ones are already pointed at the sky. There is one final number that stays with me, and I want to leave it with you. The Cosmos Webb dark matter map covers a patch of sky about 0.54 square degrees. That is roughly the area you would cover by holding a grain of rice at arm's length. In that tiny patch, the James Webb Space Telescope detected 250,000 galaxies whose shapes could be measured precisely enough to extract the gravitational fingerprint of dark matter. Behind that grain of rice, there are billions of light years of invisible scaffolding, filaments stretching across hundreds of millions of light years, voids where almost nothing exists, and clusters of galaxies sitting at the intersections of dark matter highways that were laid down when the universe was a fraction of its current age. And that is one patch, one fraction of the sky. Euclid will cover 14,000 square degrees. The Rubin Observatory will cover 18,000. The Roman Space Telescope will go deeper still. Within the next decade, we will have dark matter maps covering more than a third of the entire sky, measured with a precision that would have been inconceivable to Zwicky, or Rubin, or Lemaître, or anyone alive 20 years ago. What those maps will tell us is the question that started this story, and the question that, right now, in February of 2026, nobody on Earth can answer with certainty. The scaffolding is there. The model predicts it. The measurements confirm it. But the same measurements, pushed to their limits and compared across different methods and different epochs, are hinting that the model might need to grow. Not collapse, not be thrown away. Grow. 93 years after a difficult Swiss-Bulgarian physicist looked at 7 galaxy velocities and saw the invisible, we are still chasing the same shadow. We have gotten extraordinarily good at measuring its shape. We have not yet figured out what casts it. That is where we are. That is where this story ends, for now. And if the history of this particular mystery tells us anything, the answer, when it comes, will be stranger than any of us expect.